our progress towards the autonomous materials design with the pyiron workflow framework. So I structured this talk into 3 parts, starting with the first section on machine learning and how we apply machine learning for materials science and materials discovery. Then I will introduce the pyiron workflow framework, and in particular with a focus on how we can use workflows to digitalize our expertise, right? So like as material scientists, we have our expertise digitally to make it accessible to machine learning models. And then finally, I want to conclude with an outlook really more on the application and connecting this to experiments. So really combining machine learning, simulation, and experiments inside these kind of materials acceleration platforms. So with this, let me jump right in, right? So and I want to start here with just an application as an example in the beginning, right? So what is the kind of work that we are doing here at the Max-Planck-Institute for Sustainable Materials? I want to illustrate this here at the example of a magnesium alloy. And as you're all very well aware of, pure magnesium is rather brittle, right? So we see this here already at 10% compression. We see that magnesium fractures, and so we can't use it in a wide range of applications, right? So we would like to use it for in cars or different other applications, but we can't use it because it's so brittle. And if we look at it under the TEM, we can see these lines moving through, right? So these are our dislocations moving through our material. And as long as they move, everything is fine. But when they get stuck somewhere, that's what's causing the kind of brittle fraction. And also on a theoretical understanding, right? So we know the dislocation slip planes, and pure magnesium only has 2, the basal and the tensile twin one. But then already before our work, it was known that if you alloy magnesium with yttrium, you can activate the pyramidal slip plane. And then with this third slip plane, we can really have an alloy which can be compressed up to 50%, right? So as is shown here on the left side. So this is where we came in, and we really got the question, okay, the magnesium yttrium alloy is nice, but can we replace yttrium with another alloying element, or maybe with 2 alloying elements to be able to have a much more sustainable magnesium alloy, which ideally has the same properties as magnesium yttrium alloy. So concrete, this means we screened the whole periodic table for other alloying elements, and we look for a ternary alloy here, right? So that what we show here in terms of the yttrium similarity index, and on the x-axis as well as the y-axis, we really iterate over all the different elements in the periodic table. And we can then, what we show is the yttrium similarity index, right? So this is combining different material properties, which we found to be a very good predictor for finding the pyramidal dislocation slip plane. And now doing this kind of analysis, you directly see that this is not possible experimentally, right? So these are already millions of experiments that would be required, so that's very prohibitive. And also for the simulation side, right? So doing this kind of high throughput screening is already challenging. So then looking at the results, right? So we filtered the results in the upper half now by 95% similarity or higher. And we see, for example, these large yellow dots, right? So the large part, for example, for the lanthanide and actinides. They have very high similarity with yttrium, but they are obviously not the ones that we want to use for a sustainable alloy. Right? So these are the elements in the very lower part of our periodic table, the nuclear materials. So obviously they are not so suitable for our sustainable magnesium alloy. And then if we apply a second filter just by solubility, and then also the cost-based filter, there's just a single combination that remains. And that's magnesium with 1 weight % of aluminium and the 10th of weight % of calcium. And this is a highly ductile alloy, which we initially predicted from ab initio simulation, and which was later on realized also experimentally. So people really found the alloy exactly where we predicted it, and where we're now working on testing it more as part of the SFB 1394. But what I really find fascinating here is this rather small change, right? So we change a little more than 1%, and you have this drastically different material properties compared to pure magnesium. And how did we find this? Right, so we found this with this magnesium similarity descriptor, right? So like a lot of materials design these days is based on identifying a good descriptor and then being able to screen the periodic table with simulations, and then afterwards realizing this experimentally, right? And this is, I think that the first part, the first message I want to provide is how machine learning for material scientists may be different from machine learning in other disciplines. Let's think about medicine for a moment, right? In medicine, you develop one machine learning model, and then you can screen thousands of patients for the same kind of patterns. While in material science, we develop one model, and ideally we find one new material with this, but it's rather unlikely that we find thousands of new materials with just one new descriptor. And then if we take a look at the community, right, so there are already claims in the community that say, oh, you no longer need material scientists, right? So there's already AI tools that can do this. This claims start modest with like augmenting large language models with chemistry tools. And then they go on like something like AI scientists towards fully automated, open-ended scientific discovery, or atom agents, error design and discovery to physics-aware, multimodal, multi-agent artificial intelligence. So this really raises this question of, okay, is there still room for us as material scientists, or are we going to be replaced by large language models? Or maybe to see it a bit different, right? It's like if these papers were already as good as they claimed, we would see new materials being predicted on a daily basis. As we don't see new materials being predicted on the daily basis, I think there's still a lot of room that we can fill as material science experts, and how we can bring our knowledge together with the machine learning community and really see what is still missing, what are the parts, and how can we maybe in future get closer to this idea of jointly developing new materials design, new materials through a combined approach of machine learning and material science. Right, so I want to use the following few minutes to just give you a bit of an overview. What are the current capabilities of the large language models, how we can use them for our research, and then also to highlight a bit what's still missing and what we can contribute in terms of our expertise. And I do this here based on a PhD thesis, which is already like 10 years ago, where Ugo Aydin in our department looked at the hydrogen solubility for different metals. Right? So hydrogen solubility is very closely related to the embrittlement that we get from hydrogen. And he looked at the solubility for FCC crystals and then iterated over the periodic table. Right? So, and this is shown here. So here now I showed the hydrogen solubility over hydrogen enthalpy over the lattice constant. And we see in very first order, it's primarily a volume-dependent effect. Right? So it really follows this kind of nice energy volume curve behavior that we all know from our studies. And then in second order, it's a chemical effect. Right? So we see this jump when we go from copper to zinc. Right? So as soon as the D band is completely filled, then the energy for the hydrogen in the octahedral side is a little bit higher. So what we can learn from this is really just that hydrogen solubility as a solution enthalpy is really primarily a geometric effect, and in second order, a chemical effect, depending on the filled shells, which result in higher solution enthalpies. So that's just for us as a short reminder. Now let's take a look what the large language models already know about this. All right, so and for this benchmark here, I used the ChatGPT 5.4 model, so the latest model available, and I just asked it this question. Right, so what are the key factors for hydrogen solubility in metals, and how does the solubility change for elements in the fourth period when only considering FCC? And just for us as a reference, right, so I show again the same graph, so we can validate a bit the statements that we get from our large language model. Right, and we see here the interstitial size is already provided, right? So it first gives us a long reasoning trail, and I only show the key takeaways here. But then it says, okay, the interstitial size, so the structural property, this electronic structure, the D-band filling, just like we saw that also from the plot. And as a third part, it mentioned the thermodynamics, which is something that we didn't consider in this initial high throughput study. And then finally giving the statement of it decreases from iron to nickel to copper due to the increasing D-band filling and weaker metal hydrogen bonding. Right, so already out of the box, these large language models have a very good understanding of the general trends, the qualitative understanding of materials science. But we can also ask for quantitative statements, right? So we can ask, what is the solution enthalpy of hydrogen in FCC scandium calculated with DFT? And careful here, right? So scandium is typically a simple cubic. So asking for FCC is already quite an extrapolation. And then the answer from the model is something in the range of minus 0.4 to minus 0.6 electron volts per hydrogen atom. This is not what we see in our graph, right? So there's more in the order of minus 0.8 electron volts, but it's already somewhat in the ballpark, right? So we can learn here that these models are very good in terms of qualitative predictions, but also that the quantitative predictions are definitely reasonable, right? Also, if you would go to a material science expert and would ask them the same question, being off by 0.2 electron volts is definitely something we would expect there. So how can we improve from here? So that's what I want to show next, and that's really commonly referred to as prompt engineering. Right? So before we had just the question without any additional context, Now you can take the PhD thesis, provide it as an input, like a context for your model, and then ask the same question again. Right, and then it replies and said, okay, the DFT calculated solution enthalpy for hydrogen with NF56 scandium is 0.803 electron volts on the octahedral side, and it already gives us the right reference. So this value appears in table 5.6 of the thesis. Right, we can validate this and look at the thesis and find exactly this value. And that's really the first part that's already quite useful for me in the daily work. Right, when previously I was searching the thesis, maybe I knew it's roughly in this or maybe in that chapter, but I can do a full text search. But if you search for scandium, right, because you look for this value, searching in the table was always a big challenge. These days, I just provide the whole thesis to the large language model, ask it to go through it, and it directly finds the corresponding table where the data is recorded. Right, so large language models already on this kind of very general level help us to answer these questions. And more specifically, what we learned here is that if you ask a general question, you get a general answer. But when you provide additional context, also the answer improves. So in this way, a large language model is like an amplifier. The more you put in, the more you get out. If you put very little in or a very general statement in, you also only get a very general answer as a response. So for text, this also works, and it's already quite an acceleration for our daily work. How is it about pictures, right? So I'm a very visual person, so I want to understand how much can these models already provide us in terms of understanding of pictures. And to test this, I took a screenshot of exactly the same graph that we discussed in the beginning. And by taking a screenshot, right, so I prevent any kind of metadata to be stored in this figure, right? And then I asked the model, okay, what is the solution enthalpy of FCC scandium calculated with DFT? And that's what we see here, right? So it says, okay, 0.78 electron volts at the octahedral side. And then reading the blue points, it says, okay, in this range with a minimum close to 0.8. And so that's already quite interesting, right? So it says octahedral side. But where in the graph did it see that we're looking here at the octahedral side, right? So where did it get this information? And so we can also ask this to the model. And that's what we showed here, right? So why do you assume it's the octahedral side? And then it explains to us that based on the caption of the figure, the solution enthalpy for delta H underscore octa, it made the assumption that it's going to be the octahedral side of the model. Again, this is something when we interact with such a model in comparison to interacting with a fellow expert, we see that they act slightly differently, right? So an expert might tell us, okay, I see on this Y label, it says delta octa, and based on this, I assume it's the octahedral side, while the model directly makes the claim and says, okay, this is the octahedral side, and you have to ask it, okay, what are your assumptions to come to this conclusion? Right? So just at the moment, there's still this need for us to ask clarifying questions to get an overview of the assumptions, while we as experts, we would typically say, these are first our assumptions, and then basically give the corresponding answer or give the result based on these assumptions. And then we tried, okay, can we push this even further, right? So what is the limit of this kind of approaches? And particularly, we were interested, okay, how far can a model read this graph, extract all the data, save it maybe in a JSON file, and then afterwards plot the corresponding file again, right? So just getting a feeling of how much can the current generation of models already understand from the data that is included in graphs, right? So just imagine the capabilities that this would have of screening literature, having all kind of data, all the kind of graphs that you might have seen, all accessible from these large language models. And I save you now the Python code in the JSON file, but I directly show you the plot, right? And so this is what's shown here. And now when we compare these plots, we can already see the limitations of the current generation of large language models. Right? So we see that for most elements, they show 3 to 4 points, while the original data had 9 points. Right? So there seems to be a certain limit of the resolution, what the model can do. In addition, there's a number of elements are missing. Right? So like there seems to be the data, particularly when the data gets very close, it's not able to resolve this. And then finally, while the constant line is very smooth, the fit looks very rough, right? So it's very rough interpolation through the data. So this just highlights a bit where current models are, right? So they only are able to read roughly 20% of the data that is represented in these figures, and that's obviously still a limit to addressing our kind of data. the way to then get around this is really building these kind of large language model agents. So these are specific tools that the large language model can use to address specific questions. And so I want to show these agents, and that's really where our own work comes in terms of doing atomistic simulations. So the important aspect here is that when a large language model is able to do simulations, it can not only reproduce the data that's maybe already available in the literature, but it can also do simulations that maybe no human has done before. Right? So really making this kind of simulation experience accessible now for users who previously maybe didn't have access to simulation. Right? So we can now ask these models to calculate the bulk modules using a specific simulation method, and it just gives us the values. We can also ask for experiments, and it's not yet doing any kind of experiments, but it's just looking up experimental values from a database. But if we then look what's happening inside, these agents, we can really think about them just as like Python functions. And that's one of the key advantages here, right? So think about them like building blocks, where we as human experts, we define the building blocks, and all that the large language model is doing is based on a corresponding request from a user, putting these kind of building blocks together. Right? So really constructing then what are the building blocks I have to combine. In this case, first getting the bulk structure, and then equilibrating the bulk structure, and really minimizing the risk for hallucination of these models by having these predefined building blocks that were created from experts previously. And then also just to show this a little bit, right? So this field of large language model agents is evolving quite quickly. It started back in 2022 with the LangChain framework, and then there's the model context protocol. Now there's OpenClaw, right? So it's really very quickly moving, much faster than what we've known before on the material science side. But for us, the important aspect is really with this kind of specialized agents, we can provide the large language model with the skills to do atomistic simulations and really make atomistic simulations accessible to users who previously had no option to work with this. So we gave this in particular to our experimental colleagues, and we quickly realized that they ask very different questions from what we as theoreticians would ask. Right? So while a theoretician would ask, okay, what is the bulk modulus of a specific structure, the experimental is not so much interested in this direct relation, but more in the inverse one. Right? So they maybe need a bulk modulus of a certain range, and then they ask, okay, what is the alloying composition that we need to get there? And also these kind of questions can already be answered by these large language models. Right? So that's what I show here, where the large language model uses linear interpolation to just identify what is the corresponding composition of a copper gold alloy to reproduce the bulk modulus that the user was requesting. Right, again, I show the code, but in principle, it's just linear interpolation, what it's doing to combine these parts. Again, the important part, this is a skill like doing linear interpolation that these models already have intrinsically, so we don't have to provide separate agents, but we really just provide the agents to do the individual calculation, and the large language models can leverage this to do inverse design with these functionalities. So now moving on, we extended the base of functions and the amount of tools the agent had access to, and at a certain point, we reached the limit. And then to address this in a collaboration with the University of Michigan, we moved away from just a single agent towards more like a whole team of agents, where different agents have different roles that they are focusing on. Right? So we might have an agent for the density function theory calculations, specific agents to handle the convergent, one for the interface to the high performance computer, and one who's doing the general communication of the data between the performance computer and the analysis tools. And that this kind of team of agents works very nicely, but at some point we had the challenge that they were losing the context, right? So they weren't able to keep track of the steps and the order of steps they have to execute. So what we introduced, but really the major new feature here was having this kind of canvas where the agents can share information between each other. Right? By having a structured way how different agents can communicate with each other, they are able to maintain the general goal in mind while still focusing on a specific task in between. Previously, this was always done by providing everything in the general context, and now this can be really specific, so every agent has the corresponding information that they need for the next step of the simulation. So with this, while the functionality of a single agent was rather limited, with a team of agents, we identified increasingly complex challenges that these agents could solve. And so let me show you one of these challenges, and that's really like a benchmark that's very popular in the density function theory community. And that's, again, one of the important aspects for us, right? So we don't want to define our own benchmark and test our machine learning or our agentic framework on our benchmark, which is sometimes done in the literature. But we took a benchmark that was already established in the community, and we checked how good does the agent perform, how good does it compete against maybe human participants in such a benchmark. So that's what we see here, right? So in the first step, the supervisor comes in and writes out a plan. What are the different steps that have to be executed? Then the agent does its convergence checks, so really identifying, okay, what is the kind of basis set that I need for my simulation so that it's a reliable result, really being trustworthy, and afterwards executing the corresponding simulation. When we look at the result, the error is around 1% or lower. So this is really the point where if you give the same kind of challenge to different DFT experts, their result would also scatter at least 1%, maybe even more. Right? So if now you ask this question, if an experimentalist asks this question maybe to a DFT expert or this kind of agent, nobody's able to differentiate which answer came from whom. Right? So for these kind of standard tasks, these large language model agents are now sufficient to provide answers with the same quality of a DFT expert, which was trained during their PhD to do these kind of rather complex calculations. Right? So really having this minimum or standard quantum mechanical calculations can be executed. And I think that's really the important part here, right? So it's not about replacing scientists, but it's more of like taking the standard calculations that we have to do every day, maybe in a collaboration for our experimental colleagues, take those away and make the standard calculations accessible to our experimental colleagues without the need for us to interfere and to do the calculations, by them just talking to the agent, and for us to have the time to focus more on method development and other interesting challenges. One last statement on this: why did it work so well for density function theory? Right. So I think the main part here is we started out and we had like 50 years of method development for density function theory. So there's a very general understanding how this method scales and the different kind of challenges we have to take care of. This was followed by roughly 15 years of high throughput screening. Right? So they started with the materials project, really iterating over the whole periodic table, looking at different combinations of elements and identifying all the pitfalls of something what could go wrong. In particular, the materials project not only created the corresponding data, but they also created the corresponding tools and workflows, how to handle these challenges, right? So what are the steps, how to correct the calculation when it goes wrong? And then having this, putting the large language model agents on top of this was rather easy. Right, so I just want to emphasize this, that while it's now very successful for density function theory calculations, this is only possible based on the high throughput screening background and the workflows that we developed. So it's not, I wouldn't assume that this translates as easy to other simulation scales. So let me now take this chance and focus a bit more on the workflow aspect and what are the challenges that we have when we design these kind of workflows. Right, so the goal there is really to cover the whole process from rapid prototyping, maybe on your local laptop, to then upscaling this workflow running on local HPC, maybe up to the exascale machines. And the first thing we want is really to be like the SciPy library, right? So be able to switch between different methods, maybe different simulation tools in our case, with just changing a single variable. Right? So I show this here for the SciPy minimize, where you can switch between different minimizers by just changing a single string, while all the interfaces remain the same. Right? In the same way, we want from a workflow tool to switch between different simulation methods, even though they might be developed in different communities, by just changing the name of the simulation method, while all the rest of the variables are represented in a generic format. Second, the upscaling, right? So like, as I already mentioned, typical Python tools, they run maybe on your local laptop, but to do these kind of large-scale simulations, in particular the high-throughput simulations, we really want to be able to run first on the local laptop, then maybe a local workstation, HPC cluster at a university, and then upscaling up to the exascale machines, which now become more and more popular. And then finally, the extendability. Right? So this starts with the reproducibility, so be able to repeat the same calculations, maybe after a year or after 5 years. Then we want to have transferability. So maybe if we develop a workflow, apply it over the whole periodic table, and show that it not only is limited to one element, but can really apply to any kind of combination of elements. And then finally, as somebody who's developing methods, I'm also interested in this kind of extendability, right? So like, can I take my new method and plug it into this workflow and see how does it compete against the prior method, right? So how much does it change? And so these are really the kind of challenges. And in the pyiron framework, we really try to lower this barrier to enter material science, not only for fellow humans, but also for machine learning models in the next iteration. So how does it look like? Right? So in practice, the pyiron workflow framework is typically used inside the Jupyter Lab environment that allows us to visualize the structures and then have markdown outline of what are the steps that we want to simulate. Right? And then we first create our structure as Python code, set up our calculations, submit our calculations to run on the HPC. Afterwards, the simulation comes back, we analyze the result, and finally have the figure also in the Jupyter Notebook. Right, so if you now have the figure for all your publication, when somebody comes back and says, maybe after 5 years, after 10 years, how did you create this figure? It doesn't take you a long time to search, okay, what was the data that went into this figure? But rather you could just go back to the Jupyter Notebook and you say, okay, these are exactly the steps that I used to create this corresponding figure. And really having this one-to-one reproducibility. And we see the same already now in terms of transferability between different generations of PhD students. Right? Previously, it took a few weeks or months to train a new PhD student. Now we just give them a set of notebooks and they can really very quickly catch up. And within a week, they're definitely at the stage that they can start doing the first own research by varying parameters that maybe we haven't discussed before. Right? All this is enabled by pyiron really disseminating the kind of technical complexity for us as researchers to focus on the scientific part and the scientific challenges below. On a more abstract level, right, so that's what we show here in terms of the simulation life cycle. We as scientists, we have a model system in mind. Right? And based on this model system, we would define a hypothesis that we want to address. Right? So this might be our project. We want to validate or falsify our hypothesis. And we would do this in terms of generic input, as shown here with the blue box number 3. And everything in the gray box is really where the pyiron framework takes over. Right? So it takes this generic input, which is the Python code, and translates it to the code-specific input. So this could be a specific format of your simulation code, maybe specific units, different communities use different unit systems, different variable names, and so on. It then runs the simulation either locally on your workstation or on the HPC cluster. Afterwards, gets back the simulation results, parses the output, and again converts this output to a generic format. By having this generic input and generic output, we can do all the analysis, all the yellow boxes, independent of the corresponding simulation code. Right? So we start by validating our calculation, maybe looking for electronic convergence. We then gather the results from multiple calculations, and finally some analysis, maybe fitting a function to this. In the end, we visualize the result, and that's where the user comes back in and validates it, and maybe either says, okay, this confirms my assumption, I'm satisfied, or maybe I have to adjust my model a bit and do another iteration of the simulation lifecycle. I just show this again to emphasize what is now the impact that the large language model has. It's really just this upper part, right? So it just helps us to do the iterations of this simulation lifecycle much more quickly, while all the rest was already taken over by the pyiron workflow framework. Right, so really by covering this whole simulation cycle, pyiron is able to capture the provenance of our workflow and connect the different steps together, which then also helps us again with the reproducibility in this next step. So to illustrate this a bit more on a corresponding example, I here want to demonstrate the calculation of melting points. Right? The melting temperature is really the temperature where the solid and the liquid phase are in equilibrium, as we see it here on the left side. We then developed a corresponding workflow, and in this workflow now the red boxes indicate the inputs from the users, the green boxes are the simulation that we execute, then we have modifiers for these simulations, but the important part are really the yellow boxes, right? So we have these kind of analysis boxes also in between our workflow, so we can always keep track what is the status of the simulation, And is it really in the kind of state that we assume it to be after applying the corresponding simulation? If after a corresponding workflow step, it's not in the right state, we have this kind of feedback loop, so indicated by the black arrow, that goes back to the beginning, adjusts the input parameters, and runs the simulation again. So what are the kind of analysis that we do? Right, so one very obvious one is checking how much of the sample is liquid, how much of the sample is solid. That's what I showed here. Right, so when we visually look at the sample, we see, okay, there's roughly half of it is liquid, half of it is solid. But when we look at a common analysis tool, like the common neighbor analysis, we identify that it only detects roughly 20% to be solid. And there's a number of atoms in the solid phase which are incorrectly identified as liquid. So we then apply a kernel density score to this common neighbor analysis. And with this, we are able to identify 46% as the solid phase. Right? So really just adjusting our detector really helped us to make sure that the calculation always stays in control and is able to validate what is the state of our simulation sample after the corresponding step. In the same way, we found here this kind of pressure over strain curves, which are first nicely linearly decreasing, but then remain constant with increasing strain. And we were able to map this to the formation of voids, in particular for HPC crystals. And again, we keep track of the void by measuring the volume and compare the maximum to the mean, and as soon as it's larger than twice of the mean, we interrupt the calculation and exclude those results from the corresponding fitting. And this really allows us to then, again, have these kind of feedback loops and converge much more efficiently. As the most direct way to emphasize how this tool then works and the benefits of this kind of automated workflow is to iterate over the NIST database, which itself includes close to 200 potentials. So we did 260 melting point calculations. And just looking here at the scatter that we have from the melting points calculated for this interatomic potentials in comparison to the experimental references, we see how important it is to have these kind of tools available. Right? So while before this work, the calculation of melting points was something that one expert did in our department. So whenever we wanted a melting point, we go to this expert. They're doing the calculation and then giving us the corresponding melting point to include in the publication. It's now a tool where we just provide the inputs as a user. We start the simulation, and it automatically uses the feedback loops until it's converged and gives us really the result that we need for our part. Right, so just to emphasize this again, the automation really requires this kind of fundamental understanding of the physical processes and continuous analysis of the intermediate results. Right, so while maybe in experimental setup, we would continue, and only when something goes wrong, we would go back and check, okay, where did something go wrong? How can we optimize this? What we learned to go from automated to autonomous is really this important step of checking after every step, are we in the state that we expect? And if we're not in the state that we expect, have a feedback loop to go back, modify the result, maybe modify the inputs, to then make sure that we are directly in the state that we can analyze and work with. Now moving beyond just the classical interatomic potentials towards the machine learning interatomic potentials. Right, so the idea here is that we use quantum mechanical training data, so DFT data sets, and train these potentials on there to then calculate properties which are not accessible from DFT, like the calculation of the phase diagram shown here. Right, and this machine learning potentials are commonly constructed in two parts. One being the atomistic descriptor, which maps the local environment of atoms to a descriptor space. And then the second part going from this descriptor space to per atom energies. Right? And this second part, this could be like a neural network, a Gaussian process, or a linear regression part. And what we did here is with the FitSnap framework, where I contributed during my postdoc in Los Alamos in collaboration with the Sandia National Lab, is really to have the flexibility to choose many different descriptors and different kind of fitting engines to combine them to really design the optimal kind of machine learning potentials. So this again, right, so we previously discussed the large language models are already capable to generate the DFT training sets. The next step is then to use this DFT training sets and build machine learning potentials from them. And again, there's for building these potentials, their capabilities are very much limited by the diversity of the training sets. Right? So when you provide poor input data, you also get a poor model as a result. And when you provide a diverse input set, we can also assume our potential to really be able to be applied to a diverse range of different simulations. This was first done by the group of Danny Paris in Los Alamos, right? So they focused on maximizing the informational entropy of the descriptors to really sample the full descriptor space and get rather diverse structures. We adopted this approach and adjusted it with the automated small symmetry structure training set method, or ASSIST for short, where we start with high symmetry structures, first then relax them in terms of the volume and all the positions, and afterwards rattle and stretch these structures to really have a diverse sampling of the configuration space. This has two advantages. On the one hand, we have a very uniform sampling of the descriptor space, and on the second part, we really see that these are much smaller structures than if we want to include something like defect structures. While still, when training on these small structures, we get very good predictive capabilities on more complex structures like defects, like grain boundaries, and so on. Right? So by having these small structures of 10 atoms or less, it's very scalable, in particular also with fitting these potentials on GPUs. So now what can we learn? Right? So we apply the same kind of data-driven approach and now look at our error in dependence of the cutoff radius. And the important part about the cutoff radius is that prior to the machine learning potentials, people always assumed there's a fixed cutoff that should be the optimal one for a given element. Right? So they just say, okay, the interaction of this element should be limited to a certain range. So we really now did a high throughput study where the different lines represent different numbers of parameters, so different complexity of our descriptor. And rather than now coloring this by the number of descriptors, we colored it by the computational cost. Right? So the computational cost that it would be when you run this potential to simulate 1 nanosecond, and how many hours would it take. And then on the x-axis, you have the cutoff radius. And we can now look at an optimized Pareto front. And what we find here is it's not ideal to have a minimal cutoff radius, but rather to first go to a small descriptor basis set and keep a slightly larger cutoff radius. We can also look at this in terms of the typical plot of RMSE over computational cost. And when we compare this to a previously used potential, we see there's roughly a factor of 8 that we gain by this kind of high throughput study of the different hyperparameters of our potential. Right, just again to emphasize this, that by screening the hyperparameters with this kind of data-driven approach, we are able to get a factor 8 more scalable potential. And as these interatomic potentials scale linearly with the number of atoms, so that means with this new optimized potential, you can simulate 8 times more atoms in your simulation cell. So it really addresses a totally different scale than what we had previously possible, while maintaining the same level of precision. And the other part, again, what I said before already, right? So the cutoff radius previously was assumed to be a physical parameter. We now find it's more like a numerical parameter. Right? So when you increase the complexity of your descriptor, it also makes sense to increase the complexity, increase your cutoff radius, because a more complex descriptor can benefit from the additional information with an increased cutoff radius. So now we can put these two parts together, right? So we take our DFT calculations and try to train machine learning potential on this and look at how does the uncertainty that we have in our DFT calculation in terms of the basis set, so here in terms of the energy cutoff, affect the precision of our potential. And for the energy cutoff, this is very nice, right? So we see this nice homogeneous decay with increasing energy cutoff, and we can map this back that the structures with a high density, they have rather sharp features in the electronic structure. And when we have these sharp features in the electronic structures, this also results in an error when we go to lower energy cutoffs. Right? So we can identify a set of very dense structures, use those to estimate the uncertainty of our error, and then already include this in our machine learning potential. On the other hand, if we look at the K-point mesh, so the sampling of the reciprocal space, the behavior is much worse. Right? So it's not even homogeneous. So this really raised the question during my postdoc in Los Alamos, how can we use this diverse sets and still benefit from DFT calculations at lower levels of precision? And to show a bit the advantage of these lower levels of precision, we have two sets here, right? So we have the low precision set, where one configuration takes us roughly 20 seconds. And then we have this high precision set where every configuration takes roughly 1,000 seconds. Right? So a factor of 50 that we can gain. So you can see that we can benefit quite drastically if we can leverage the low precision calculation rather than relying on the expensive ones. So we split our set 50-50, 50% training set, 50% testing set. And we looked at the RMSE between these two sets, just comparing the two DFT levels. And this was 5.6 millielectrons. And then we did our typical metrics, right? So training on low precision and predicting on low precision, and training on high precision and predicting on high precision. And we see the regular behavior, right? So like training error is always a bit lower than the testing error. But now when we do the different step, right? So we train on low precision and we predict on high precision, the resulting RMSE error is lower than the error that we had in the training set. Right? So this is first very surprising, but we can understand this because of the fluctuations in the DFT test data that we have on our testing set. Right? So if we go to higher precision, there's less fluctuations in our testing data. So that's why we get a lower RMSE when we compare to the high precision data versus comparing to the low precision one. Right? To make this a bit more visual, right? So we can look at it not just in terms of the RMSE number, but really in terms of the distribution of the uncertainty, where we see when we train on the low data and predict on low precision, fit it on high precision, and fit it on the error on high precision, and now bringing everything together. Right? So this the green curve is now the case when we train on low precision and we predict on high precision. And what we find here is the same what we also found on the DFT scale, is that there are two contributions. First, one systematic contribution, that's the shift of the distributions, and then a statistical one, which is basically the width of the distributions. Now putting all this together, and that's what I show here, right? So that's basically now on the x-axis, we have the force error. On the y-axis, we have the energy error. And then we show this in terms of the computational costs that we need for the quantum mechanical calculations, or the DFT calculations here, to build the corresponding training set. Right? So think about this as the total computational costs to create the corresponding machine learning potential. And we can pick one point, and we can see here, if we want to decrease the error that we make in the forces, we can do so by just adding more and more configurations of the same level of precision. In contrast, if we want to go from the energy error and decrease the energy error, we really also have to improve the level of precision to go to a higher level of DFT calculations. That's really the cost-intensive step. And what is even more important, if we now transition and we may be restricted in terms of the computational costs that our potential can have at the end. Right? So let's say you want to do a very large-scale simulation with this potential afterwards, and you're limited, then we see that these potentials with less complex descriptors benefit much less from the advantages of high-precision DFT data. Right? So that's really the key message here, that maybe for a lot of training sets, people at the moment invest a lot of time in high-precision DFT data, while the limiting factor is actually their machine learning potentials. And so they could get away by using much less converged DFT data for training their potentials. Now, putting this together, right, so I talked about the training data set generation, the potential fitting, and the validation step. The fourth step here is now calculating properties which are not accessible from the DFT calculations. Right? In our case, we are very interested in calculating the full phase diagram now with these machine learning potentials. And on the left side, you see the result that we get from our machine learning potential, which is basically just based on the electronic interactions, the interaction of the electrons. That's the only empirical parameter that goes in there, in comparison to the experimental phase diagram represented by the Calvert model. And we already see a nice qualitative agreement, and we're now working to also getting a more quantitative agreement, right? So there's still some work in progress, but we now have with these workflows, we have a tool to systematically address this. With the machine learning potential, the goal with there is to be able to predict the full phase diagrams from ab initio, to have a descriptor that helps us to identify the elements that we can design. Right, and going back now to the high-level picture, what we see here is now that we use machine learning primarily to couple the different scales in material science. And that's also the aspect that's so interesting from the people coming from the machine learning community, But they say material science is interesting because of this hierarchical nature of materials, and which is a perfect benchmark to see the coarse graining of the machine learning potentials. Right, so really this intrinsic hierarchical approach really requires us also to have hierarchical simulation approaches. Obviously, we are also not the only ones who develop workflows and address these challenges. So back in 2023, we sit together with other workflow developers in our community, primarily the team from the AIDA from Switzerland and the JobFlow community from the Materials Project. And we thought about, okay, how can we generalize these workflows even further? Right? So we identified, okay, the first step is that all these workflow frameworks nowadays use Python functions as their primarily building blocks and then combine them. So we first agreed to say, okay, we want to separate these Python functions, separate our parsers from the underlying workflow framework. And then as a second step, we agreed on the Python workflow definition, which is now an exchange format. So you can write a workflow with one of the three frameworks. You can export it to the Python workflow definition and then import the same workflow in any of the other frameworks. Really also enabling collaboration between the different workflow frameworks to, again, accelerate the sharing of knowledge within our community. The final step, and that's still work in progress, is really this idea of sharing not only the workflow, but also the underlying data, right? So that's still a bit more challenging. So we haven't addressed this completely yet, but that's really the next step. Not only share the workflow, but also the attached results between the different workflow frameworks. Just to highlight again, right? So we don't try to do this in a closed environment, but really leverage workflows for the community to really be interoperable. And just to again show this again on a small example here, right? So I show two Python functions and how we would call them. These Python functions in the Python workflow definition would be stored in the Python module. And then the calling of the Python functions, that's where the workflow definition applies. And that's what we then store in the JSON graph. Right, so you really have this kind of workflow graph, separating it into nodes and edges. And based on this representation, make it interoperable between the different workflow frameworks. Right, all this is work that we do as part of the NFDI Matwerk Consortia, really trying to, again, focus on the interoperability within our community. So now let me come to the last part and use the last few minutes to show a bit how do we now connect this to the experimental side. Right, and the big challenge there is, as I illustrated in the beginning, is this iterating over the whole periodic table. And that's where our collaborators, so the group of Alfred Ludwig at the Ruhr University Bochum, made a lot of progress in producing these kind of materials libraries with chemical gradients inside them. Right, so I show them here. There's a typical approach that's a combinatorial decomposition, where they sputter different elements from different directions and always sputter one element at a time. The challenge with this is you have this kind of layered thin films afterwards. So you need processing to get a homogeneous, atomically mixed gradient. And what the group of Alfred Ludwig developed is this kind of co-sputtering approach to really get fully mixed thin films already in one step by sputtering from multiple elements at the same time. Right, so this co-sputtering really gives us this nice chemical gradients, which then allows us to iterate over the whole periodic table by having all the mix in there. Right, so then the next step is how do we measure these kind of wafers with the chemical gradients. Right? And here I just show once the experimental setup. On the left side, you see the measurement devices. In the middle, you see the robotic arm, which is moving over the wafer. That's also highlighted on the right side. And then in the middle at number 7, that's the computer interface for the user. All right, and then on the right side, we really see how the robotic arm goes over the wafer and does different measurements at different positions where it represents the different concentrations. All right, so again, I show this here. In this wafer, we now have what's indicated with yellow, like high concentrations of given elements. And when it comes to the dark blue, the concentration is much lower. And here shown for a 5-component alloy. And now the robotic arm iterates over this, as I show it here. And typically, this is like a sequential measurement over the whole sample. And that really, now they have the sample creation addressed, but really highlights the challenges now on the measurement side. Right? So you need 400 individual measurements. And if you do, for example, XRD measurements, measuring one of these material libraries can easily take 12 to 14 hours. Right? So really the measuring part becomes the limiting step. And that's when they came to us and asked this question, okay, how can we now accelerate this process, and can we benefit from your experience on the high throughput simulation side? Right, so we know that's what we call these kind of materials acceleration platforms, where we just connect the experimental equipment as just another source into our workflow framework, and then try to combine the simulation approach and the experimental data into one machine learning model. Right? And in very simple terms, it's just like calling another Python function. So the workflow framework doesn't care so much if it's now a robotic experiment or if it's a simulation experiment on our computer. Right, so that's what I show here. Again, the same chemical gradients of the different concentrations. And then we have the experimental measurement, and below there's the theoretical calculations that we did. And really, now we bring both of these data sources into the same experiment. If we do this naively, just coupling both, this doesn't work so well. But what works very well is using the density functional theory data to optimize the hyperparameters, and then use this optimized machine learning model. In this case, it's just a Gaussian process to predict on the experimental data set. And with this, we are able to reduce the number of measurements from the prior 400 measurements down to 20 measurements. Right? So really just 20 measurements that drastically reduces the time. It really gives us the opportunity to measure many more of these materials libraries. And again, this is possible by combining both the machine learning and the DFT simulation to then reduce the number of experimental measurements here. Maybe as an outlook, what we also learned in this project is a bit that there's a challenge in terms of the different user groups. Right? So on the simulation side, we were able to make a lot of progress by providing a Python interface and really doing this kind of data-driven interface to simulation. What we now learned is that maybe on the experimental side, that's a bit more challenging. And what they would really like to have is more like a visual representation of what's happening underneath. In particular, when we consider the large language models, which can very quickly generate large amounts of code. Right? So similar, like I showed this here for the tensor test, right? So like they really want a visual representation where they can access the different steps. So that's what we are currently working on as like a prototype on our side. You can now provide the text of what the steps you want. The artificial intelligence then generates a workflow, and you see the resulting workflow in this kind of visual programming interface. You can validate it's the correct one, or you can correct it. And then afterwards, you can start the simulation. Right? Really trying to, again, address this challenge that people maybe get a response from the large language model, but don't know what it is. Now they get it as a visual programming interface. Then they can interact with it. And only once they approve it, then we run the corresponding simulations. So really with this programming interface, the user validate and modify the suggested workflows from the large language models. All this is obviously not only my work, right? So the pyiron project is an open source project. We have contributors from many different universities in Europe, but also internationally. We regularly organize hackathons. And we're very grateful for all the funding for digitalization in Germany, particularly the AFDI Mathwerk and also Materials Digital community there. And there's a growing number of users, but also a growing number of external contributors to our open source projects. With this, I come to my conclusion. I hope I was able to show you a bit what are the capabilities of large language model agents and how they will allow us to bring our expertise as material scientists into this new environment. How workflows really help us to digitalize our expertise and how we can document it with a tool like the pyiron framework. And then gave you a little outlook that maybe experimental equipments are also just another Python functions. And these material acceleration platforms greatly benefit from the combination of simulation experiments in the same machine learning framework. And with this, I'd like to thank you for your attention.
Thank you, Jan, for this very impressive presentation. I have learned a lot. Now I'm more convinced to, turn over to pyiron and then try to get it installed.
Yeah, I'm happy to help.
Good to know. Are there questions or comments? So you can switch on your microphone and ask directly, or if you have technical problems, you can type in your questions or type the questions in the chat. So I will read it. Everyone is shy. Okay, let me start. So then you mentioned such kind of evolution of the large language models in terms of launching, like this MCP and OpenClaw. So are you thinking of converting workflows to actually scale?
Yes. So basically, what we find is that the workflows are very similar to what the large language models do with the agents, right? So like the agents are also just like different steps that the large language model connects.
Yeah.
So that's what we as humans previously called workflows. And we're now still working on what's the best layer to bring both together, right? So with the length chain part we started, it's also similar to these kind of Python-based functions. But we now see with this more modern approaches like the OpenClaw, that you only need like a markdown file describing the functionality of a given functionality. So that might even be a much simpler way and much more scalable way to bring more and more of our expertise also to the large language models to then be able to use it for a much wider community and not just the experts who can write these Python workflows.
Yeah, I think then you mentioned that such Jupyter notebooks can be used to train the new generations of PhD students. I think then actually I'm thinking of getting such skills, developed corresponding to the workflows, but then in a more modularized way, so that we can have, one skill corresponding to only one functioning unit in the workflow, so that we can then also try to benefit from all such existing, like kind of OpenClaw like platforms, right?
Yes. So I don't want to claim that we have the perfect solution there yet, right? So we are also learning. And what we definitely saw on the way is that this community is moving very fast. Right?
Yeah.
So like in our community, we all use the same DFT code for the last 20 years or something, right? So like that is rather slow development, while in the community around these large language model agents in the last 4 or 5 years, right? So it's changing every year or at least every other year. But it's getting easier, right? So I guess it's going in the right direction. It's just not yet converged. And we have to see how much time we invest on which technology and at which point it makes sense to switch from one framework to another. But I completely agree, right? So breaking it down to small parts and then making it accessible to both human users and machines, that's the future direction.
Yes, very interesting. So meanwhile, I see a question in the chat. So Yagyang, would you mind switching on your microphone and directly ask, or should I read? Okay, so let me read the question. It was great talk and I learned a lot. Can you tell me if you have tested machine learning intelligent potentials on low symmetry materials like the 5-component battery cathode materials you showed?
So the battery example was done with pure DFT calculations. So that was not done with machine learning potentials, primarily because we wanted to get the electric resistivity, right? So that was the property that we optimized there. We have work on high entropy alloys for an application for machine learning potentials, so that's definitely possible. So I think there's no limit, and I think in particular with the new generation, so the group from Ralph Trout's just recently released a new Grace model, which is now trained on this on the SMAX dataset. So that's from the group of Danny Paris. So that's one of the first ones trained on this highly diverse dataset. And we've seen very good performance for those, right? So it's even the question nowadays, should you fit your own model, or are the universal potentials getting good enough that there's no longer the need to build your own machine learning potentials?
Yeah, I think this will also bridge us to the seminar in 2 weeks, which will be given by actually Professor Gabor Sayi, who is moving to Mainz. He could definitely tell us about what he thinks.
Yes, he's definitely much more of an expert on the machine learning potential than I am. I am already looking forward to his talk.
So Aaron, please.
Hi, thanks for the great talk. I have a short question. about the cost of the agent's orchestration. I suppose you're using an API for using ChatGPT 5.2.
Yes.
So can you tell me like an estimate of how much it costs to run a workflow for a simulation?
So I guess this a single workflow is not so expensive. The expensive part is the development of the workflow. So at the end of the hackathon, we won a prize money of like $1,000, and we invested this money to develop the second generation. Right? So like it's currently not so easy to get separate funding and just invest it into tokens. And that's why we did it with this kind of prize money and then invested the prize money again. We are also seeing more and more improvements from the open models, right? So the open source ChatGPT model is already much better, but still there's the commercial models still give us an edge. So it's hard to put a number on like what is the cost of one iteration, but I can tell you the paper, the Dreams paper, we spent $1,000 in terms of token cost.
Thank you.
Yeah, I think as Jason Huang mentioned, like in the future, I think it's a business of tokens, right? So then like in this regard, I mean, depending on the volume of the context you want to plug into the model, it might be costly. But
Yes.
I mean, if I were doing this, I would then try to, employ a local model just to get the functions done. This can be done with such open source code as Jan mentioned, like Quinn and so on. And then after doing this, you can then try to proceed with the testing using the cloud or whatever. Yeah.
Yes. And then also like in Germany, like for the universities, we have this GWG, right? So the Göttingen Institute, which provides free access to a large number of open large language models, right? So they provide API keys. So if you're a student or somebody working at a German university, you can get free access provided by them. So they have locally hosted LLMs with API keys and everything. So that's a very nice service that we also start to use more and more.
This is fantastic. Good to know. Okay. Any other question? If not, let me take this chance to ask another question. So then like, what is your, so you mentioned like such kind of prompt engineering, context engineering. I think nowadays, as you said, people are talking about harness engineering and so on. So then like, what is your overall feeling? I mean, I think this question is more or less overlapping with the point we discussed about how should we think of the future. But my question is more or less, do you think we have already the final solution, or should we wait for some years to see how the direction of large language model is developing?
Yeah, I don't think that we have the final solution yet. I think it's important for us as community to identify what are good benchmarks to validate the progress. And for us, the plot that I showed is one of these benchmarks, right? So we are now at 20% that the large language model can read. We were much poorer a few generations before, right? And even the recent changes make a jump. So that's something that we continuously test. Okay, what is the capability of these models for different tasks? When the example that I showed was like searching a PhD thesis for a table where a certain value is discussed. This is nothing I can do with like a full text search, right? So because if I search just for the element scandium, it's mentioned hundreds of times in the whole thesis. So I will have a hard time to go to the specific table. But with the large language model, I just provide the thesis and the question, and it directly finds me the right table. So that already speeds up a typical task that I have. I know this is somewhere in this thesis. I don't know where exactly. It's faster to give it to a large language model and ask the question rather than me trying to search it. And in this way, I guess we have to go step by step and see where do these models actually help us. Similar for the standard DFT calculation, right? If before you need to train somebody to get access to standard properties, sure, we can store this data in databases like the materials project. But if we go to like 4-component, 5-component alloys, you can't build a database for those, right? So there's the number of combinations just explodes. That's where these kind of agents come into play, because suddenly everybody can do the calculations themselves and still have expert level quality of the results. And I think that's maybe the most important part, right? So I think once the model gives you a wrong prediction, that's when you lose trust in the model, right? So then it breaks down. So I think our task as theoreticians and people working with these models is to minimize the risk of hallucination, so that when our community is accessing these models, we maintain this trust. If you directly go to a model, you might get poor performance. What we can achieve with these agents, it's much more reliable results. And then I guess it's a progress of time. I can't predict what we will see in 5 years, right? Maybe the whole trend reverts because the cost per token gets so expensive. But if the cost continues to decline, I will estimate that we use them even more in the future.
But this hallucination problem can be partially solved using this retrieval augmented generation, right? So then,
Yes.
yeah, but then of course, nowadays I doubt that people can do like a reg with all the literature on even one subject. So then you need to really get selected literature papers fed into the large language model, so you can then try to train a useful one.
Yes, I would really say, right? So like, we should still maintain the general overview of the literature. But let's say you read a new paper, you want just a quick summary of the paper, or you know, okay, it's somewhere in this review, they discuss this in detail. So should I now search for it, or do I just give it to the large language model and tell, where did it discuss it? Which paper should I read when I'm interested in this particular aspect? And so I see it more as like an assistant, right? So it's not yet on the PhD student level, where you can give it a task and it comes back after a week and presents you some solution. It's more like a master student, where you have you give them a question and they come back after an hour or two, and then you discuss the next step and so on. So the independence is still rather small in terms of the time it can operate until it needs new feedback from you to do the next step. But I hope this is going to improve over the upcoming years and with the next generation of models. And what we can already see is that the current reasoning models are much superior to like what we had before. So I think there's still a continuous improvement, which makes me optimistic that we'll see even better models in the near-term future.
Yeah, I'm also interested at the development from such technical gains. Whether do we have more powerful large language models? Okay, so